states.
Thanks. Okay, so yeah, my name is Sumeet. I'm a student at LSU, and I'll be talking about some work I've been doing with Mark and my collaborators, Ludovico Lamy and Gerardo Odesso at Nottingham in the UK. All right, so to start off, before I dive into the work that we actually did, let me start off by presenting to you the following problem. All right, so consider some collection of particles. Say here we have 10 particles, which are labeled using the yellow circles. And suppose we're given the states of some subsets of these particles. So here we have row 1, 2, 3 that describes the state of particles 1, 2, and 3. We have a state that describes the correlation between 3, 4, and 5, and so on. And the question that we want to ask here is, does there exist some global state? So does there exist a state rho tilde on all the particles, such that when we take the reduced density matrix of this thing, we get the given states that we have here corresponding to the subsets of the particles. And the question about the existence of such a state is called the quantum marginal problem. And this problem is interesting not only from a mathematical point of view, but it is also interesting from a physical point of view. Because one can imagine that instead of just having 10 particles, we could have a many-body system, a large number of particles. And it would be nice if we could somehow infer some global properties of the state by just looking at reduced density matrices, by just looking at properties of some subsets of particles without having to find the full density matrix. And this is a problem that has existed for several decades. And let me just flash up an example of this from 1963, where they look at the structure of fermion density matrices. And the author of this paper starts off by asking the question, can the wave function be eliminated from quantum mechanics and its role be taken over in the discussion of physical systems by reduced density matrices? So this is exactly this question. And in quantum chemistry, which is the context in which this is being asked, it's called the N representability problem. And this is a difficult problem. We still do not know the conditions that must be satisfied by the density matrix. So in other words, we don't know the conditions that must be satisfied to determine whether there exists such a global state. And the existence of this global state, as I said, is called the N representability problem, which he states here explicitly. How can we recognize that an alleged two-particle density matrix is in fact the reduced density matrix of a system of n indistinguishable particles? So here this is in the context of fermions, but this exists even for bosons and just in general. And it was shown that, and so this problem has existed for a while, and it basically hasn't been solved in full generality. It is known to belong to the class of QMA since 2006. So, given the context of this problem, and given that it's difficult, so one aspect of this problem that shows up, and which is what I'll be talking about primarily, is the following problem. So suppose we have now, focusing on this side here, we have sort of k plus 1 parties. So we have A, which we can think of Alice, and we have some collection of B parties here. And suppose we're given the reduced density matrices corresponding to A and each of the individual B's. All right, and not only that, but we suppose that all of these reduced density matrices are equal to each other, and they're equal to some given state, rho AB. Now we want to ask that question from the beginning. Does there exist a global state such that when I take the corresponding marginals, I get back just this given state? And if such a state exists, which we call rho tilde for all the parties, then we call such a density matrix or such a quantum state a k-extension of the given state. And so this is the focus of our work. An alternate way to define this k-extendibility is by saying that this global state, if it exists, is invariant under any permutation of the B's. So I can do any sort of swapping that I want among the B's, but the global state will always stay the same. Furthermore, we want this to be an actual extension of the state, which means that if I trace out all of the B's except for one, then I get back that given state we start with. All right, so we have now our definition of k-extendibility of quantum states. All right, so, and one of the reasons in which is, I mean, it turns out that this is important not only in this context of quantum chemistry. I mean, it turns out to be a special case of the quantum marginal problem, this particular k-extendibility problem. But it's also important because as we increase this k, it turns out that if the state happens to be k-extendable for all k, then it's separable. So it's not entangled. And so this parameter k can be viewed as some kind of intermediate parameter that sort of gives us the interpolation between, some interpolation between things that are entangled and states that are separable. So as we increase this k, we sort of get closer and closer to the set of separable states. And one of the questions that arises in the setting of k-extendibility is, can we actually quantify this distance in some way? So can we put some bound based on k as to how close we're getting to the set of separable states as we increase k? So this is how the k-extendibility problem relates to entanglement, because all states that are not in this region are entangled. All right, so given all of this context in which k-extendibility is relevant, when is a quantum state k-extendable? So how can we figure this out? Okay, so we start by supposing that we have some state, rho AB, and we fix some k greater than or equal to 2. And the goal is to find some positive semi-definite matrix, which we call rho tilde as before. So it's positive semi-definite such that this marginal constraints are satisfied for all k. And this is a semi-definite program. So as long as the dimension of your matrix is not too large, you can easily plug this into some software like MATLAB, and it'll tell you whether or not it is k-extendable. All right, but what we would like is to be able to not, and I mean the important thing is that if the dimensions get too big, then it could be that you can't even store this rho AB in memory. So it would be nice in some contexts to be able to come up with some analytic condition that tells us, just as a function of the given state alone, whether or not it is k-extendable. And in this domain, very few results are known. So there's a full characterization in the case when we set k equal to 2, and in the case where the given state is a 2-qubit state. In this situation, this inequality is necessary and sufficient for true extendability. So this has been known since 2014. But as soon as we step away from this, as soon as we increase the dimension of A or B, and as soon as we step away from k equal to 2, much less is known. So in higher dimensions, we have some partial results, and there are many papers one could solve for some partial results, but I can point you to one of these here. So now the question is, what about infinite dimensional systems? So systems that we see in, for example, quantum optics, right? Such systems are described by infinite dimensional Hilbert spaces. So naively, one might think that now, we have to deal with some infinite dimensional matrix, right? So, yeah, so this is basically the question that we deal with in our work. So we study the k-extendibility of states of continuous variable systems, and we obtain an analytic necessary condition for the k-extendibility of such states for all values of k. And when we restrict ourselves to this special case of Gaussian states, then we're able to obtain an STP that kind of looks like what we have here, except it's finite dimensional and it depends only on the covariance matrix of the given state. All right? And when we restrict the number of modes on the B system, so this is the state, this is the system that we're extending. If we let that be just one mode, then we can basically solve this STP analytically. And we obtain an analytic necessary and sufficient condition for all values of k. It's kind of like this kind of thing, where it's like some inequality, except it holds for all k. And so one of the consequences of one of the corollaries you can see of this main result is that we can place a bound on the distance of any k-extendable Gaussian state from the set of separable states. So this is the kind of thing I was talking about earlier, where you have this sort of nested layer of 2 extendable, 3 extendable, and then as you get k to infinity, you get to separable. So we're able to place a bound on the distance as a function of k. And we can place a bound on the entanglement of k-extendable Gaussian states as a result of this. Because any state that's not separable is entangled by definition. Okay, So before proceeding, let me just talk a little bit about continuous variable systems, just to fix the notation. I'm sure many of you already know most of this. So we start with the position and momentum operators for our system of n modes, and we put them all into this vector R, and we order them in this particular way, which is helpful. And we define the mean vector of any given state and its covariance matrix in this way. So this is the first moment of the state with respect to these operators, and this is essentially the second moment. And it is a known result that for any quantum state, you have this inequality satisfied by the covariance matrix, where this omega is this sort of anti-symmetric form. All right, and this inequality is important. It's satisfied by any quantum state. Okay. And when we restrict to Gaussian states, what we mean by that is that the corresponding characteristic function is a Gaussian function, and it is completely characterized just by its mean and its covariance matrix. Furthermore, you can, for faithful Gaussian states, which are those that are positive definite, they have no zero eigenvalues. You can write them in this sort of exponential form for some quadratic Hamiltonian. So it's quadratic in the quadrature operators. An example of a Gaussian state, for example, is a single mode thermal state, where here n bar is the mean number of photons. Okay. All right. So now let's jump right into the problem of k-extendibility of states on a continuous variable system. All right. So we start off with any bipartite quantum state. It doesn't have to be Gaussian at this point, so it's just any state. All right. And we let its mean vector be this, and its covariance matrix be this. Now, the particular way in which you ordered the quadrature operators means that we can actually write the covariance matrix in this form, where VA is the covariance matrix of rho A, which is the reduced state, and VB is the covariance matrix on the B system. And X, we can think of that as describing the correlations between them. Okay, so before we tackle this problem directly, we can make a couple of reductions. So the first thing is that we can restrict ourselves to zero mean states. The reason for this is that we can always take any state with some non-zero mean and use local displacement operators to set the mean to zero. So by D here, I mean a displacement operator or a while operator, and just by subtracting off, in essence, the mean vector, we can set the mean to zero. And because we're doing this using local unitaries, the k-extendibility of this shifted state will be the same as the original one. And this is due to the fact that k-extendibility is invariant under local unitaries. And the way you can think about that intuitively is that by just applying local unitaries, you're not going to be changing the correlations between A and B. So it makes sense that the k-extendibility wouldn't change. So if this is k-extendable, then so is this, and vice versa. All right, so we can just set this S vector to 0. Okay, and the second reduction is, and this is something that one has to actually show, but I'll just state it here. So if this state is k-extendable, then its covariance matrix, so then the covariance matrix of the k-extension can be taken to be of this form. So where we remember that X is the same matrix from before that describes the original state, and Y is some real and symmetric matrix. So I should maybe just mention, because I forgot to, that the covariance matrix is a real and symmetric matrix. And in particular for this case, if due to the properties of the k-extension that I showed at the beginning, we can always take this Y to be symmetric. So we don't need a Y transpose here. It's just 1. All right, and because the k-extension has to correspond to a valid quantum state, this inequality should be satisfied. All right, so we know that if it's k-extendable, then there has to exist such a Y, such that this is satisfied. All right, so there's one more reduction that we can make, and this is actually one of the results of our work, is that if we take a Gaussian state, then it is k-extendable if and only if its k-extension is also Gaussian, or if there exists a k-extension that is itself a Gaussian state. And this is actually an important thing because we can then, for the case of Gaussian states, just restrict the search for k-extensions to just Gaussian states. So we can take the k-extension itself to just be a Gaussian state. And that's important because then we can reduce the problem of determining the k-extendibility of a Gaussian state to just looking for k-extensions that are Gaussian. So we can just impose this. And this is now an SDP strictly in terms of the covariance matrix of the original state. And we can do this because of this result, which is that if the k-extension exists, then there exists one that is itself a Gaussian state. So this is our first result. Now, so this is the case for Gaussian states, and now we can take this a little bit further and obtain our main results. So this is for any state. So if it's k-extendable, so now this is a necessary condition. If it's k-extendable, then there exists a real symmetric matrix called a delta sub B, such that these two inequalities are satisfied. Where here we have again the covariance matrix of the original state matrix. For Gaussian states, because Gaussian states are completely characterized by the covariance matrix, this condition is necessary and sufficient. So this condition becomes necessary and sufficient for the k-extendibility of Gaussian states. Now this still doesn't fully solve the problem. In essence, this is still just an SDP, because we still have to know whether or not such a delta exists. But in the case when the B system just has one mode, then we can solve the problem fully, and we can say that it is k-extendable if and only if this inequality is satisfied. And so all we have to do is plug in the covariance matrix of the given state, Gaussian state, and the particular value of k that we're interested in, and this gives us a way to determine whether or not it is k-extendable. Okay, so what are some of the consequences? Okay, so so how do we prove this?
You should mention the k-extendable.
Yeah, that'll come. So how do we prove this? So I'll just go through a brief sketch of this. So what we want is for basically this matrix to be positive semi-definite. This plus I times omega to be positive semi-definite. And the main tool that we use is what's called the Schur complement. So this is just some result, we can think of it, just some result from linear algebra, which tells us that if we have a block matrix of this form, then it is positive semi-definite if and only if this particular matrix is positive semi-definite. And I should mention that not only this, but P should be positive definite and hence invertible, which is why we can take its inverse. And this thing here is called the Schur complement of M with respect to P. All right, so we want this matrix to be positive semi-definite, and so we can partition that matrix into blocks in such a way that we can actually make use of this theorem. So here we can recognize the block P, here we have the block Z dagger, and this red block here basically corresponds to Q. So all we do is we recognize that we can partition the relevant matrix that we're interested in such that we can use this result. And as soon as we do so, we get this inequality. And we make the definition, we just define delta to be VB minus 4. So then we get this inequality. Now, the leftmost inequality is already part of the result, so that's this result right here. To get the second inequality, we look here, and we just apply the Schur complement result in sort of reverse, and that leads us to this inequality, which is the result, and that's it. Right? So this proof now holds even for the Gaussian case, just by letting the given state be Gaussian. We just know that it's going to be necessary and sufficient because for Gaussian states, the covariance matrix fully describes them. Okay, so now what about the case when the B system has only one mode? Then this inequality contains only 2 by 2 matrices. In the existence of a delta B such that this inequality holds, that can be determined from a known theorem. So that's the inequality from the previous slide. Now we can make use of this known result, which is that if we have 2 matrices that are 2 by 2 and Hermitian, Then there's just a real symmetric matrix R satisfying this inequality, which is just like that one, if and only if these two inequalities hold. Where here by M bar, I mean the complex conjugate of M. So you just take every matrix element to take its complex conjugate. All right, so if we apply these two inequalities, then we get this. And after simplifying, and now we can again recognize that this thing right here is essentially just the Schur complement again. And so we again apply the Schur complement in reverse, and we get this. And that essentially completes the proof of the main result. Okay, so now let's get to some of the consequences. So some of the corollary results. So the first thing is the fact that, yeah, so this is the result. So the first thing is now relating back to this diagram I showed at the beginning of the talk, which is the sort of thinking of k as this parameter that tells us how far we are from the set of separable states. And we can see here that if something is, for example, 3 extendable, then it's also 2 extendable. What this means is that if we take this condition and take the limit k to infinity, then we should get the condition for any given state to be entangled or separable. So if we just take the limit k to infinity here, then we'll just end up with this. So we'll end up with the statement that the given state rho AB is separable if and only if there exists a delta such that this inequality holds. And so what, and this reproduces basically the null result about separability of Gaussian states. So that's good because that's what we would expect for this type of result to give us. All right. So some of the other things I asked about at the beginning of the talk are, okay, so how can we basically quantify now the distance of a given k-extendable state to the set of separable states? So that's what we can do next. So firstly, how do we quantify the distance to the set of separable states? So there are basically two ways that we can do that. One is just using the trace distance, which I think we've seen before today. So basically all we do is, this is our given state, and this notation just means a set of all separable states where the sort of bipartition is between A and B. So yeah, and so we think of, yeah, so all we want to do is we want to find essentially the closest state from the set of separable states. So we use the trace distance as our distance measure here. Another common distance measure that one uses is based on the Renyi relative entropies. Here we'll let alpha be between 0 and 1. In the case when alpha is equal to 1, we obtain the usual von Neumann relative entropy. So this is an often used entanglement measure, and it can be used in the context of quantum communication protocols, for example. So using the result that I showed, we can prove that if we ask the question how far k-extendable Gaussian state is from the set of separable states, then we can come up with these upper bounds. So we can see here, so here the upper bound depends on the sum of the two modes of A and B, so NA is the number of modes for A and B is the number of modes for B, divided by K. So one simple thing to check is that as K goes to infinity, this thing does approach 0, as you would expect, because we already know that as K increases, we get to the set of separable states. The other nice thing is that about this inequality is that it only depends on the number of modes. In fact, this is true for both inequalities here, right? So we have some similar looking inequality for the relative entropy of entanglement, which is what it's called. And again, for alpha between 0 and 1. And this depends only on the number of modes. So in the case of finite dimensional quantum systems, similar inequalities are known, but there's like there's a dimension factor up here in those inequalities. And the interesting thing is if you just took those on face value and applied them to this, then D would just be infinity. But the nice thing here is that we obtain something that is finite. It depends only on the number of modes. It doesn't even depend on the energies or anything like that. It just depends on the number of modes, which is nice. All right, so we have a couple of other results on the entanglement of formation, but I think this suffices. So I'll just summarize. So what we did in this work was obtain necessary and sufficient conditions for the k-extendibility of all Gaussian states, and we were able to formulate this as a finite dimensional semi-definite program. So one that is depending only on the covariance matrix of a given state. And when the number of modes on B is equal to 1, then we can fully solve this STP and obtain some condition that we can just plug into and see whether or not your state is k-extendable. And we use this condition to obtain bounds on the distance to separable states and to quantify the entanglement of Gaussian k-extendable states. Some directions for future work. We would like to obviously extend this characterization that we have in the case of one mode to more than one mode. It also turns out that this distance, the distance to the set of k-extendable states based on a different kind of distance measure, similar to this one, can be used to bound the non-asymptotic quantum capacities of quantum channels. So one of the things we would like to do next is to use those results to find non-asymptotic quantum capacities of single mode Gaussian channels. And with that, I'll end. Thanks.
Questions?
Have you thought of any connections to the Hornberg-Kohn theorem and Helix end representability? Because we are sitting here in New Orleans, close to Tulane and John Perdue and Mel Levy, and there's an enormous amount of work because there you have a similar system of a one particle density and everything, particularly of the ground state, if it's being extended even more, can be represented in terms of one particle density.
So you mentioned the n representability problem.
Right.
There was something else?
That's the one I was thinking of as an analog of what I hear when you talk about this.
So, what exactly? So, sorry.
So in statistical mechanics, you have, of course, an n-particle system, and you have these density matrices of different numbers where you integrate out successive ones, and then you come down to a one. And there is this Hornberg-Kohn theorem that the ground state of a quantum system of n particles can be completely given by the one particle density.
Oh, I see. This is in the quantum case, or
Yeah, in the quantum. That's the famous
what I
density
do-
functional
okay.
theory. That's
Right. So what I do
It's
know.
formally that it exists, that there is such a thing. Now, what that functional is may be complicated.
Right.
But formally, it
I
is
see.
proven by the
So that's something I would have to look into.
Well, there's a comment actually. I also wanted to ask a permutation of this question, but so there is a theorem that says that's the density, which means in this language it's diagonal element of the density matrix. There's a theorem that says that there is no single body density matrix that is a function of energy. So somehow for density matrix the thing does not work. Only for diagonal density matrix it works. Means like there's no one-to-one correspondence between energy and one body density matrix. So it's a kind of really non-trivial question.
So yeah, what I was going to say is that for fermionic systems, so this is in this paper that I had at the beginning, what is known is that for fermionic systems, the question of the ground state can be reduced to the question of two body density matrices. So in that case, that really is a specific context in which this shows up. So I'm not sure if there's an instinctive thing that matters as electron correlation should show up in the two particle density matrix. And I think now, since then, I think it is known that for the ground state energy of certain kinds of Hamiltonians, it suffices just to look at the two party density matrices.
But you're saying that's specifically for fermionic systems.
I believe it is for fermionic
And
systems.
is the implication that bosonic ones are more complicated? That would surprise me.
I'm not sure if there's
I think
any.
it's the other way around.
All I know is that for the fermionic case, this is the result that I remember. I'm not sure about the bosonic ones. It is true in our work we just looked at bosonic states. And we looked at a particular case of the quantum marginal problem that's really of this very specific kind.
We could probably look at fermionic Gaussian states and
Yes.
extend a lot of this theory.
Exactly. Yes. Yes. Other question?
Actually, is there an analog of this in kind of classical statistics, like ordinary statistics?
Yes. This problem exists even for like classical probability distributions.
But is it
Now
not
this
so?
problem.
But those can be trivially extended.
Yeah, those can be
Those
trivially
are like
extended,
separable states, they can be trivially extended.
So there is no. It's not solvable, right? Meaning that it's only separable state. There's no other way. Right?
There's nothing
Separability is the only unique solution in classical.
It suffices to solve the problem, right? Somehow it's not very interesting compared to what can happen with entanglement in the quantum case.
Yeah, and then the really interesting situations show up really because of the existence of these overlapping margins. So if these marginals weren't overlapping, then in some sense it kind of reduces to a classical case, and the global state you can take as just a tensor product of the subsets. No subsets.
Any other questions?
There's a reference to showing that this problem is QMA complete.
Yes.
Maybe you discussed that a little bit and I missed it, but what does that mean exactly?
So it belongs to this class of QMA, Quantum, Merlin, Arthur. So what this means, so I don't know it too much in detail. All I know is that it's kind of like the quantum analog of NP, the complexity class NP. So what this means is that if someone gives you a global density matrix and asks you to verify whether or not it is indeed corresponding to these marginals, then you can do that easily because you can just take the partial trace. But I believe that problems that belong to this complexity class are sort of believed to be difficult to solve. So I think it belongs to the same class as like the k-stat problem for Hamiltonians. Yeah, I believe it's in the same class.
And one more thing, so you have these, there's this result that says if something's k-extendible for all k, then it has to be a separable state.
Yes.
Was that for the finite dimensional or was that for infinite dimensional also?
So yeah, that's a good question. So this, strictly speaking, as far as I know, this result is for the finite dimensional, and then it was extended to the infinite dimensional.
Okay.
That's Partha-Sarathy.
Right.
Okay.
Yeah. So the second part was out. Yeah.
So I have a question.
Yes.
So I think how this method is different from the variational inference method. It's just like probability.
I'm not familiar with that.
Okay.
What-
Basically, yeah, you define a probability distribution for definite set for each of them. Then you try to optimize to find a global probability distribution so that you can extract the information for each of them.
So that is as if you're doing like tomography.
Yeah,
so if you
it's
have
just like
some-
a inference. You are trying to define as a whole probabilistic distribution for the given number of sets.
That sounds like the classical version of
Yeah.
representability, right?
Yeah.
So yeah, it's not so if it just reduces to classical probability distributions,
Yeah,
it
because-
has to be in some sense.
Yeah. Can you go to the one slide where you define the trace distance? I think it's in the last.
This one.
So yeah, in here you define the two distance and you are optimizing those distance, right?
So
and-
this one.
Yeah, and the second expression you have infimum d alpha rho
Yes.
ab, and at that point you are trying to calculate the inference between the sigma b and rho ab, right? Because you're trying to match the probability distribution between
But
the
this is
rho
not just a
and the
probability.
sigma.
These are not just probability distributions. I guess they're quantum states.
Yeah, because you have distance on rho ab minus sigma ab. That means you are trying to.
It's quantum relative entropy.
Okay.
So it's, the first one is trace distance, which you can think of as like a measure of how well any experiment could do in distinguishing the quantum states. And the relative entropy is related to that also. So it really is a quantum measure.
Yeah, it's quantum. I think it's a quantum version of Kuhn's divergence theorem.
Yeah.
Yeah. Okay.
Yeah.
I have one last quick one. How close are you to finishing for NB equals 2? Or are you doing that? Or have you started that?
Yeah, that's something we're looking at, I guess. I mean, that's something we don't have it, but yeah. That's something I'm just.
Do we expect to get there? I mean, like, we have the SDP. You can solve
Yeah,
it
you can.
numerically.
Yeah, if you have any particular state, then we have for Gaussian states we have this STP. So you just have to sort of. This is the STP for Gaussian states. So
Because I think that's very relevant to the stuff that Wendy was talking about. For NB equals 2.
Yeah, so for NB equals 2, we don't have a nice closed form inequality like this one. But if you have some state, and maybe if the number of modes for A is not too large, then it can